Okay, we'll get started here. Are there any, so before you get going, so the exam, you can currently see it up there on Canvas. Go to files here, not files, sorry, go to quizzes. Kind of see it's here as the exam. You could also go to assignments, and it kind of shows up down here. It is, so I think I had the numbers a little wrong after I finalized it. There's 22 questions, each one's worth 4 points. There's also a 23rd kind of bonus question. So you notice it says out of 104 points here. It's actually just out of 100. There's basically like 4 extra points in the exam you could get. So you could get 104 out of 100. The short answer question is worth 12 points, has 3 parts to it, each worth 4 points there as well. For that part, I want you to show your work. That way I can give partial credit, even if you don't get answers correct on that part. Once you start it, you'll have an hour and 20 minutes. Actually, 1 hour and 20. I'm going to give you guys a little bit more time. Let me see. Oh, there we go. Let's see what it actually says. Yeah, so hour 20 minutes. I think it should be more than enough time. As I said, there's a couple extra questions, but some of the ones I added are actually pretty easy, so I think they'll help kind of cushion the grades a little bit from what I had before. If you have any technical problems, email me right away, like, so we can try to get something figured out. Don't wait till, don't try to like kind of work your way through it. Like, I don't know if for some reason you're 5 minutes in and it submits it, right? Like, don't let me know 3 hours later. Like, let me know as soon as something happens. Like, hopefully nothing does happen like that, but if it does, email me as soon as possible, okay? You don't have to have a lockdown, so you can have Excel, you can have your formula sheet open. The only kind of thing I ask you to do is, respect academic integrity. Don't kind of, after you've taken the exam, don't talk to anybody else about it until after Tuesday. Other than that, I think we should be okay. Are there any questions for me before we kind of jump into some practice problems? Anything related to the exam? Okay, all right. Let me see. So, are there any specific problems that anybody wants to start with? If there are, I'll start with those. If not, I guess I'll try to kind of choose. Yeah. 24. Okay. So these are some uniform distribution ones. If we want the probability that person waits between 15 and 20 minutes here at the BMV, and we're kind of given this information up here at the top, right? So we know that the waiting time is uniformly distributed from 0 to 60 minutes. So right away, we should be thinking about is we have this uniform distribution, and it goes from 0 to 60. Okay? You want the probability that's between what, 15 and 20? I believe that's what the question said. So, we could do this as easy as we're looking for the area of a rectangle. So what's kind of the base here? 20 minus 15 times what's the height of this distribution? We said we always know the height is 1 over, think about this as max minus the min, which here would just be 60 minus 0, or 1 over 60, right? So if this is, ends up being what, 5 over 60. Go back to the answers here. Should be, oh, there's a typo. What should this be? Is the answer C here in the answer key? Let's see. This is the wrong one. Practice exam A. Yeah, I think the decimal just got put on the wrong side there. Yeah, so it says 24 should be C here. Sorry about that. I'll put an announcement up. Right, that should be 0.083. Right? So that 0, we're missing a 0 there. Does that answer? Is that kind of the problem you're running into?
Yeah, I just thought I was.
No, it should have been 0.083 there. kind of using the method I just talked about. Any other questions on those? Okay. Yeah, if you run into a problem like that, like I said, there shouldn't be, hopefully there's no more typos, but if you're running into something like that, let me know. So I can get kind of things cleared up as soon as possible. All right. Any other questions on these binomial ones, since I know that's what we went over Friday? I think, the mean and the variance should be pretty easy. Your binomial equations are the only thing here on that second part of the formula sheet. So the mean is just, maximum plus the minimum divided by 2. The variance, maximum minus the minimum, squared divided by 12. We'll follow those two equations every single time. So that should be 21, 22. Hopefully those are relatively easy questions if you saw those on the exam. Other than that, it really is comes down to, I think, drawing out that uniform distribution and thinking about what area you're looking for is probably the easiest way to do it. Yeah.
How would you know you would have to use that variance equation for this certain amount?
So if we look here, the information that we're given, right? So this is kind of the end questions here. So for the rest of the questions, we're using this idea that the wait time is uniformly distributed from 0 to 60. So as soon as we know that this variable that we're looking at, this wait time at the BMV, is a uniformly distributed variable, we know that the equation that we can use for the mean and the variance for a uniformly distributed variable is right here. Okay? Just like if we had a binomial example, which I think is what we have up here, right, with these credit card examples. Excuse me. Then we know that we can use our binomial equations, which now we have our mean and our variance equation for a binomial random variable. And I don't have it in the formula sheet here, but it's something that we talked about. What should the mean and the variance for a Poisson be? Remember, I had this unique property where the mean was equal to the variance, and the mean and the variance would just be whatever this lambda is, right? That average rate that you're given, right? If the average rate, you're told what the average rate is, and you're looking for the mean, well, the mean is just the average of that error. So, you're given that information, okay? Any other questions you want to start out with? Either practice exam A or B. Check the chat here. Nobody? Has any questions? So we should just leave right now? No. Okay. So let's look at what I'm going to be. I think I'll do one that I think is useful. Well, we'll start with this. Let's do these contingency table ones. So I had this example. I told you to watch the video. I don't know if any of you did on the Comedy Central idea, but this idea that wages are kind of linked to looks, right? And so that if we took these individuals with the hourly wage, we said, is it below $8 or at least $8? And we took their looks rating from 1 to 5 and says it below 3 or at least 3, right? So we've got a couple missing parts here. So how would I find the missing value for X? We said when we're looking at these contingency tables, these top 4 left cells represent intersections. But how do I come up with the totals? Yeah, just add across the rows or down the columns, right? So here I can take everyone who has a below 3 rating and makes below $8, everyone who has at least a 3 and makes below, and that covers everybody who makes below $8 an hour. So if I just add those two together, I would get my total there, right? Which represents the probability that someone makes below $8 per hour. So to get X here, I would just add across. So 11.11 plus 0.67 should give me 0.88. Right? I'm just adding across there. So adding across the rows. That one shouldn't be too bad. And let me help you. What did I write in there? Hold on. Oh, 7, 8, my bad. There we go. I'm looking at these numbers, right? 0.11 plus 0.67 will give us, if I can type here, 0.78, right? So that should give us X. What if I wanted to find Z? Well, it's the same idea, but now it's 0.11 plus Z would give me 0.13, right? So what has to be the missing point there? Well, I could type this out if I really wanted to. what did I say? What was that 1, 3? Right? I can do a little bit of algebra here and find out that z would have to be 0.02. Okay. So that's how I can find missing components in this table. Hopefully that's not anything crazy there. Any questions on that? Saw something come up in the chat. No, you don't need to show your work for the multiple choice questions on the exam. That's why I give the short answer just in case if you're making mistakes, I can give you some partial credit there. That might not come up on the rest of the exam, right? And like I said, I've done exams where I have a lot more short answer, and grades typically end up being about the same. Because sometimes when I can see your work, I can understand that you're clearly guessing, and so you lose points there. Whereas, you know, if you make a stupid mistake and get one wrong, so it kind of balances each other out. I shouldn't have said it like that, but you get the idea. Yeah.
But, for like the response, we should show what you calculated.
Yes. Show your work so that way I can give partial credit on those as much as I can. Yep. And those are some a little bit harder ones, and so that's why I want to see the work there so I can give some of the more partial credit. What's the best description for the missing probability? Well, hopefully at this point, when we see a contingency table, we should think these all represent intersections. So this would be the probability that someone has below 3 looks rating and makes at least $8 per hour. So here we're looking for that. So probably that someone has looks of less than 3, not 4, not given, and has a wage, right? If I'm writing this out in terms of my probabilities, and I'm thinking about what an and represents, I should be thinking, right, if I'm writing A and B, that was kind of our symbol, right, the upside down U. But in words, the intersection, we use that word and. Okay. All right. What's the probability that someone has looks of at least 3 or a wage below 8? So this is one I don't think we did in the other practice exam. So here I'm looking for the probability of a union, right? An or. Okay. So I'm just going to write out what I think this looks like for our problem. So we've got what? The probability that looks is at least 3. So probability that looks is greater than or equal to 3. Or second thing is that wage is less than $8 an hour. Okay? So here's our event A. Here's our event B. How can we find this? Well, it's not one specific cell in our contingency table. So we go to this formula sheet. Go up here. So, okay, how do I find the intersection? Or not intersection. How do I find the union? The union of A and B is take the probability of both events, subtract what I double counted, which is their intersection. So I could just look at this and write it out in the context of my example, right? So here, I'll take the probability of A, so that looks is greater than or equal to 3. Add that to the probability of B, which is that wage is less than $8 an hour. And then I'll subtract out the intersection of those two things. So I run out of room here. Less than $8. Right? Now these are just totals in my contingency table, and this is one of those top 4 left cells. Okay. So I'll move this guy here for the video if anyone's watching an After Effects. So I can find these 3 components pretty easily from that table. Right? So what's the probability? And I'll leave this up here for the video here. What's the probability that someone has looks of at least 3? So I go at least 3, 0.87, right? So I plug that value in. What's the probability wages are less than $8? So below $8, go to the total. That was actually something I had found earlier, 0.78, once I figured out how to add. And then the third thing I wanted was the intersection of those two. So below $8, looks of at least 3, plug in my 0.67 there. Now it's just a little, enter that in our calculator. It should be pretty easy. 0.87 plus 0.78 minus 0.67 should be what? 0.87 plus 0.78 minus 0.67. Should be at what, 0.98 there? Okay. And that kind of makes sense because remember what we also said you could do. This isn't like the good way to do it, but if I want the union of two events, I can find the intersection, make an L, and then add those up. What do those add up to? 0.87 plus 0.11, 0.98, which makes sense because the only thing that wasn't there would have been that 0.02, which we found earlier was Z. Now I would use this way instead of kind of making an L, but you know, if it's easier for you to remember that way, you can do that as well. Okay? This is the more like technical one. Any questions on that one? Okay with that? So I could ask you to find a union. Did I skip one here? What's 9? Okay, I can work on this one. Let's be good. So what's the probability that somebody has wages above $8 given that they have looks greater than or equal to 3? So the way that I would always write out these conditional probabilities is, what am I given first? So I'm given that looks are greater than or equal to 3. What's the probability wages? Is it above $8? So greater than 8. Well, I can't get a conditional probability directly from my contingency table, but what I can do is say, well, look, I know that I can find a conditional probability by the intersection of those two events divided by whatever I'm conditioning on. Okay? So I'll rewrite this. So wages are greater than 8 and looks are at least 3. And then I divide by the probability of whatever I'm conditioning on, or probability of B, right? Whatever's on the right-hand side there. I can get these things directly from the table. So now I just want the intersection of having high wages and looks. So I go, get rid of this here, move myself back over here for the video. We'll go up. Wages of at least 8, looks of at least 3. That's 0.2 divided by the probability of having looks of at least 3. That's what I'm conditioning on. 0.87. So it should be about what, 0.23 if I do that math. So we'll go back down to 9. Should be A there. Okay. Any questions on that one? So all I'm doing there is using the multiplication rule. When I want to find this conditional probability, I can't get that as one value from my contingency table, but I can find different components from my table to be able to solve for that. Let's make sure there's no questions in the chat. Okay. We're okay with that one? Yep. So this is the, showing you a completely different table. But here we're thinking about two definitions, mutually exclusive and independent, right? Hopefully, when I'm thinking about whether or not events are mutually exclusive, this should be a relatively easy one, okay? The only way two things are mutually exclusive is if they can't happen at the same time, right? So when I'm thinking about this visually, this is where we said, here's A, here's B, right? There's no overlap, right? So if there's no overlap, what does the intersection have to be for mutually exclusive events? It doesn't exist, so the lowest probability you can get is 0, right? So we're looking for if the intersection of these two events is equal to 0, they're mutually exclusive. Well, I know that my contingency table shows me the intersection of these events. I see no zeros here. So, unless I see a 0 in that contingency table, nothing's mutually exclusive. If I see a 0 in that table, then those two events are mutually exclusive. So here it's pretty easy. We can think about the complements. If their intersection was 0, they'd be mutually exclusive. It's not, it's 0.3. So they can't be mutually exclusive. So we either know that this is going to be the right answer or this is going to be the right answer, right? Because those are both ones where they say they're not mutually exclusive. So the second thing we have to check is this idea of independence. Okay, so the idea of independence was if the probability of A was the same as the probability of A conditioned on something else, right? Now in here, I'm thinking about the complements. Well, that doesn't change much for me. I could just say is the probability of A complement the same as the probability of A complement conditioned on B complement. Okay? If that's true, they're independent, right? Because it doesn't matter whether or not I know B complement has occurred or not, the probability of A complement doesn't change. That means they're independent events, right? So I can check this from the table by saying, okay, what's the probability of A complement? 0.4. Okay, so I'll go back to the screen here in a second for those of you on Zoom, but give me 1 second. And then if I want to find the probability of A complement given B complement, I can rewrite this, just like we did earlier, as a conditional probability divided by what I'm conditioning on, right? So I could go here, I know this was what? I think I said it was 0.4. Yeah, this was 0.4. How can I find this? Well, I could rewrite this as the probability of A complement and B complement divided by the probability of what I'm conditioning on. What's the probability of A complement and B complement? 0.3 divided by the probability of B complement, which is 0.75. What's 0.3 divided by 0.75? 0.4. They're the same thing. Okay? So the probability of A complement here is equal to the probability of A complement conditioned on B complement. So here we actually have events that are independent because that equality held. Okay? So these events are independent, but they're not mutually exclusive, which I think was D there. Yeah, that was answer D. Right? So that's how we can check kind of mutually exclusive and independent events. You know, like I said, to me, the mutually exclusive one should jump out at you right away. I mean, spoiler alert, it wouldn't be a very interesting joint probability table if I gave you had a 0 in it. So that one will probably, I don't know. It's unlikely to see mutually exclusive events when we're dealing with problems like this. But the independence one, we still always have to check, right? And in this case, they are independent. Okay? Yeah.
What does independence mean for two events?
Right, so if we're thinking about it here, let's say A complement, or these could be A and B. Let's say the example I always give, because as far as I know, eye color isn't related to gender at all, is that what's the probability that if I chose someone at random, they had blue eyes? All right, it's like 0.15 or something. And then I say, okay, given that I'm now telling you the person you chose at random is male, what's the probability they have blue eyes? Well, it doesn't change anything, right? These are independent events. Like and I say this as though I know this scientifically. I'm not a biologist, so but I think that that's true. That gender plays no role in kind of eye color. And if that's a bad example, please someone let me know. But I think it's good. I like it. It makes sense. This thing doesn't matter, right? These things are completely, one of them occurring doesn't impact the probability of the other occurring. Now, a lot of things that we'll look at are not independent, right? Most events you can think about probably are in some way a little dependent on each other. Any other questions on that before we keep moving? Okay with those? Any other specific ones that people want to kind of start with? Otherwise, I might just start picking and choosing a few. Let me see if there's any up here that are interesting. I'll mention that before we leave. We could work through this one. I think we'll work through this one. Do you guys want to see a Bayes theorem one, or I don't know, want me to work through this kind of general discrete random variable? Bayes? Okay. That's what I figured. So let's say we have this information, and this one is probably a little bit more obtuse in the explanation than I would give you on the exam. But according to this data from the National Health Survey, 33% of white women are obese, 41% of non-white women are obese. Nationally, 48% of women are white. So I would not give you information like this on the exam, I would change these into the terms of, I would give you some word of given, right? So the idea is when you're told 33% of white women are obese, we can think about this as, you know that given person or the woman you're looking at is white, the probability they're obese here based off of data is that 33%, right? You then kind of have the exact same thing, but now you're told the individual is non-white, you would know the probability is 0.41. Right? So this is based off of some survey data. You might be interested in kind of health differences across races. And then we look at nationally, if I were to choose someone at random, the probability that that person is white, right, is a little bit below kind of half the population. Okay? So this is what we're starting out with. This is what we're given. Okay? Now, like I said, if I'm doing this on the exam, I would have written it out this way for you. Let me type this out. I would have given you information like this. Right, so that's a little bit easier. I'm giving you that word given. You can think about writing the conditional line and be a little bit clear how to come up with those probabilities. Okay. So now that I have this, all right. So number 11 is what's the probability that a woman is white and obese? Like someone I selected at random. So what I would first start out doing, and I'll type this one out and go back to the board here in a second, is just write down what you're looking for, right? So here's my two events, right? And I could, if I wanted to, if I'm writing this out, if I don't want to use this word and, I could write that little, set symbol in there instead. And now that I know I'm looking for the intersection of two events, I know I can find the intersection of two events by the conditional probability times what I'm conditioning on, okay? So I'm going to keep this up here on the right-hand side and try to kind of type this out in the context of my example. Okay? So I know that I can rewrite the intersection as a conditional probability times what I'm conditioning on. So my A is the individual is white, my B is the individual is obese. So I can go the probability of B, which is that they were obese, given, I'll put a space here, that they're white, right? I'm just kind of writing out this multiplication rule in the context of my example, times the probability of whatever A is, so that our A was that they're white. Well, now, if I remember what I had up here on the board, the probability someone was white was 0.48. Given that someone was white, the probability they were obese was that 0.33. So 0.8 times 0.33, should get about 0.264. Why is am I reading this wrong? Probability that they're white is 0.48. Given that they're white, the probability they're obese is 0.33. Why is that not lining up to what I have here? 0.8. Oh, because did I write this down? So I've got B given A times the probability. Why am I looking at this wrong? So A is probably the woman is white and obese. So we write probably obese given white times the probability they're white. Oh, because I typed in my calculator wrong. I had 0.8. Sorry, yeah, 0.1, so 0.16, yeah. Yeah, it helped. So 0.48 times 0.33, not 0.8 times 0.33. I was going to say, everything looks right here. Yeah, so once we plug our probabilities and assuming we can use the calculator correctly, we should be good, okay? Any questions on that one before we keep moving? Now this one would be the exact same, right? Which is instead of white, everywhere we would have white, we would have non-white, and then we'd just be plugging in these other probabilities. I'm not going to work through that one because I think we've got an example like it, and you could maybe try to work that on your own. I think the next one's more important that we get through before we run out of time. If we have time, we can come back to this one. So what's the probability the woman is non-white given that she is obese? So here, what are we looking for? Say given someone is obese, what's the probability that they're kind of I say non-white, I want to keep it, yeah, non-white. Or we can think about this, we could, minority or however we want to kind of denote this. Well, here I'm looking for a conditional probability, right? The format of these exams are pretty similar, and you might have noticed once you get to this last question, a lot of times you have to use that Bayes equation, right? I could try to rewrite this conditional probability as the intersection divided by what I'm conditioning on. I'll notice that what I'd be conditioning on is the probability that they're obese. I don't have any of that information given to me originally. And so it's probably going to be a pretty good indicator. I'm going to have to use this Bayes theorem, this Bayes equation over here. Right? So once I identify that I'm looking for a conditional probability, I would think about, here's my S, here's my E. Right? Now I'm just going to write this out in the context of my example. Okay? So go down here. This is going to be equal to, I'll make this a little bit easier to see as I type this out instead of writing it on the board here. Okay. I'm going to delete this for a second so I can get everything up on the, oh, that's going to change the number. Give me 1 second. So we can see everything. There we go. Okay. So I'm going to write this out in the context of my example. Okay. So the first thing I want is the probability of S. So I have my S right here. So the probability non-white times the probability of E given S. So obese given non-white. Now the nice thing about this equation is the very first part of my denominator is the very same as my numerator, right? So I'm just going to copy and paste. For you, that would be basically just writing down the exact same thing that we just had. If I can select this one. There we go. All right. The second part of that denominator is the probability of S complement. Well, here, my first state of nature is kind of this S of being non-white. S complement would just be that the individual is white. Right? Times the probability of E given S complement. My E is that the individual is, by the standards of whatever organization we had the survey from, that they're obese, given S complement, which our S complement was then that they're white. Okay? But once we have this equation, notice, what's the probability somebody's non-white? Well, I wasn't directly given that, but if I know the probability that someone is white, what would the probability that they're kind of non-white be here? Whatever gets to 100%, right? Those categories are created so that they're kind of only two states of nature, right? Now, obviously, in practice, like, we could break this group down into multiple different kind of races, but for here, if we're just looking kind of difference between majority, minority, right? It doesn't matter what it is. We could be talking about gender, we could be talking about race, we could be talking about eye color, whatever we want, right? We split it into two groups, two states of nature, okay? So now I've got the probability that someone's non-white. I can plug in the probability someone's white here. Given that someone's non-white, what was the probability they're obese? Well, that's right here. So you can plug in 0.41 right here and right here. And then given that someone's white, what's the probability they're obese? Right? So I can plug in my 0.3 here. So that's kind of how I would approach this. So I guess if we're going to do, make this a little bit, I can kind of plug the values in for you here so that we can see what this would look like. So right, the probability they were non-white was what, 0.52 times, given that they were non-white, the probability they're obese is 0.41. 0.52 times 0.41 plus 0.48 times that 0.33. Now, this one, isn't an example I would probably use on the exam. It's thinking about how we could do this with something that doesn't quite look like a test kind of outcome thing. Something I do in the exam a lot more like here's the disease, here's whether or not we see a positive or negative test, right? But really what this is saying is, look, if all the information I have is that someone is obese, and I know that obesity rates maybe vary across kind of white and non-white individuals. I know that pool of people that are obese, it's not like a 50-50 split. And so they're not independent events. It gives me some information about whether or not the individual would be white or non-white, right? So it's the same kind of idea. If I see a positive test result, well, there's plenty of people who have a positive test result who actually have the disease, but also some that don't. And I might want to, I'm probably interested in what that ratio is, right? And this is really what Bayes' equation is trying to get at, okay? Any questions on this before I keep moving? I don't think, is there another question on this one? No? Okay. Now, one thing I would suggest, I think I might suggest this last class, maybe looking at those two examples I did in that additional Bayes video would be really helpful. Wink, wink. One of those examples might look really familiar once you start the exam. I would also say something to review. So up here on number 4, I likely won't ask you to calculate a covariance or something like that, but kind of going back through your notes and remembering what covariances and correlation coefficients tell you. So the idea there was a covariance, right, is kind of unitless, you know, doesn't have, you can't compare across examples, but once I have that correlation coefficient, it's unitless, and I know it ranges from 1 to -1. The closer to 1 represents a very strong positive relationship. The closer to -1 representing a stronger negative relationship, and how we can kind of compare across examples there now because they're unitless and we've scaled them. So that might be a good thing to review before you go into the exam. Let's see, is there anything else that I would mention or kind of want to go through here real quick? Got a little bit of time left. I would remember, so I think there aren't any Poisson examples here, but I would go back through the day we talked about the Poisson, specifically when I talked about how to make rate changes, right? So if you're given the average number of accidents over an hour is 5, if I want the average accidents over a day, what would I do? I would just take that 5 and multiply it by 24 hours in a day, right? So I can make these conversions to longer time frames by multiplying lambda by whatever the conversion factor is. And if I wanted to go, say, from the average over a week, and then I said, well, what's the probability that 4 occur tomorrow, next day? Well, if I have the average over a week, how do I get lambda over a day? I would just divide by 7. So if I want to go to a smaller kind of time frame, that was where I'm dividing by whatever that converting factor is. Okay? And then once I have my new lambda, now it's just a matter of plugging it into that Poisson equation. So I would review those. Also, one of the videos I posted up, I did an additional kind of Poisson example at the end that wasn't on that practice exam A either. Okay? What if the other thing I would review is, I'm making an example off the top of my head here since no one has specific examples over some of these practice questions. What if I wanted the probability, let's say that on average, we'll do a whole example here. So okay, nope, actually I'm gonna do something different. We're gonna flip this around. So I tell you over a week that 14 occur. Now the probability that, let's do this. I can combine a bunch of different things into one thing here. So I tell you, let's say the average number of accidents out in the Galliard every week is 14. What's the probability that I see at least one, occur tomorrow, right? Or in one day, okay? Well, first of all, if I'm thinking about the probability over a day, first thing I have to do is get my lambda that I want, right? So that lambda, let me show you, no, I can't see that, so I'm gonna write down here. Lambda for a day would just be what, 14, right? Going from a week to a day divided by 7 or 2. Right? Now here, if I want to find the probability that x is at least 1, so greater than or equal to 1, I'd have to find the probability that x is equal to 1 plus the probability x is equal to 2 plus the probability x is equal to 3. Where do I stop, right? I however many cars I guess there are in Muncie in a given day. Well, that's not practical. So what's another way I could do this? If this is event A, I know I can rewrite this as 1 minus the complement. What's the complement of being greater than or equal to 1? Less than 1? What's the only outcome that fits this criteria? 0, yeah, right? So really this is just 1 minus the probability x is equal to 0. And so now I have to use that Poisson equation only one time, where x would be 0 and lambda is 2. Right? Once I find that, subtract it from 1, and now I'm done. Right? So the rest of that is just computation. So we would go back, x is equal to 0, go to our formula sheet, plug in x is equal to 0, lambda equal to 2, compute that on our calculator, subtract it from 1, and then we have the probability 1. Okay? So that would be one where like I'm combining a bunch of different stuff into one problem. I would just want to do that so you could think about, I could ask like one question where I give you the average over a week, and I say, okay, what's the probability that 3 occur in the next day? So you might have to find the probability exactly one number. But then I could say, okay, what's the probability of seeing greater than or equal to, right, or less than or equal to? And sometimes using that complement rule is really going to be the only way that you can do that efficiently. Okay? Any questions on that one? Yeah.
Is there any more examples like on the exam practice that have like this kind of scenario, like dividing like if it's like a week or a day? Or...
So I would say that I think on the practice exam there aren't, but the one day we went through the Poisson in class, that would be one to kind of review if you want to review that. Another good thing to look over if you're looking for more stuff to review, other than practice problems, is, and actually, because that's too far, I'll make sure that the answer key's up there as soon as I get back from class today. But you can start to review Excel number 2, because that had some contingency table stuff, and it also had a Bayes theorem question at the end. So I'll get that answer key up there. So if you're looking just for more problems to go through, you could do that. Yeah, other than that, kind of, got that one I worked through in the YouTube video, the additional Poisson question. But really, if you understand the principles behind the binomial questions, it's the exact same thing for the Poisson, other than the rate change. Yeah. Any other questions on those? Okay. Let me see. Is there anything else I want to mention on these? Yeah.
We can do 14 and 16. I think it's on
Oh, here? On B or on A? Yeah, so this one is probably, or maybe over simplifying it. So if I see that I could see, here's the number of homes sold in the next month, either 0, 1, 2, or 3, right? Each one has a different likelihood of occurring. If I want the mean of this random variable, what I don't want to do is simply add up the possible outcomes and divide by the number of outcomes I have, because that's treating it as though everything's equally as likely, right? So what I want to do is factor in that the likelihood of seeing 1 house sold is very, very likely, while the likelihood of seeing 3 is very small. Okay? So if I look at my formula sheet, when I have just a general discrete random variable, not a binomial or a Poisson, but just kind of this small subset of, small set of numbers that the outcome could be with your associated probabilities, I'll go through each outcome, I'll multiply it by the probability that outcome occurs, and then add them all up. So it's very similar to a weighted mean, except now we don't have to divide by the sum of the weights. We said if the probabilities are our weights, the sum of the weights will always be 1, and almost ignore the denominator. So here all I would do is 0 times 0.3 plus 1 times 0.5 plus 2 times 0.15 plus 3 times 0.05. All right, so 0 times 0.3 plus 1 times 0.5 plus 2 times 0.15 plus 3 times 0.05. So if I do this, I'm guessing we get 0, 0.5 plus 0.8 plus so 0.95, I think is what you should get if I'm doing the math in my head there correctly. Okay. Now, if I simply add them up, right, 0 plus 1 plus 2 plus 3, I get what, 6 divided by 4, and we got 1.5. But that's not factoring in the fact that some of these values are more likely to see than others. And if I wanted to find the standard deviation, well, the process to get the standard deviation, I first have to find the variance and then take the square root. Well, here I've got the variance equation for this discrete random variable. It's the exact same as I would do a variance for a normal variable. I take the outcome, subtract the mean, square it, but then I need to multiply it by the probability that I saw that outcome occur. So now it would be 0 minus that mean of 0.95 squared times the probability I saw 0 occur, or times 0.3, plus 1 minus that mean of 0.95 squared times the probability I saw 1, so on and so forth, right? So, I don't know, if we're kind of getting an idea here. We would start out, that first outcome minus that mean of 0.95. So I almost had to find 14 here to find 15. So times 0.3, and then plus the next outcome, which is 1, minus that mean, squared, times the probability I saw 1 occur, which is 0.5. And then we'll do the other two outcomes as well. Right? Now, one thing that I will probably do on the exam here is I usually would say, what's the standard deviation of this variable, assuming the mean you found was 1, right? I might, or maybe 2, right? So that makes it a little bit easier. So instead of 0.95 every time, you can just be putting 2 in. If I give you an assumed true value though, don't read into it at all. It may not be anywhere near what the true mean actually is. I'm just giving it to you so you all start on the same foot, and maybe just to make the calculations a little bit easier. So I have to put a 2 in my calculator or whatever instead of 0.95 every time. Okay? Any questions on that one? Yeah.
So those were for the random variables.
So whenever you have kind of these outcomes that have probabilities associated with them of occurring, right? Yeah, and that represents a discrete random variable. Yeah.
0.95 means that the mean for the average home they sell monthly is 0.95.
Yeah, and to say it a little bit more correct, we say it's the mean, but it's also the expected value, right? Because this discrete random variable is something that hasn't happened yet. So if we look at the next 20 months, the average number of homes we would see sold is 0.95, or the expected value in the next month would be 0.95. Is another way of saying that as well. And the standard deviation in the number of homes sold the next month would be, I don't know what it is here, whatever the answer keys, right? If we compute this out, whatever that ends up being. Right? Any other questions? The only other one here, we'll just end on this, I think it'd be pretty easy. What's the probability they sell at least one house? So write down what you're looking for. At least one would be the probability X is greater than or equal to 1. So all you're doing there is what outcomes fit that. So it could be 1, it could be 2, it could be 3, and then add those probabilities up. So the only thing you have to really be careful there is the equality, right? If it's just greater than 1 home, I wouldn't want to include 1. Here it's at least 1 home, so it's 1 and everything higher. So we'd add those probabilities together, 0.5 plus 0.15 plus 0.05, and get that 0.70. Okay, I kind of cut out from our last lecture. I'll also get that up on YouTube, the Bayes theorem of question we worked on Friday. So that that video will be up on YouTube as well. I'll get all this recorded lecture posted later this afternoon. If you have any other questions before you take the exam, feel free to reach out, email me. You can start it anytime today or anytime tomorrow, except you have to start it by at least 10:40 if you want the full hour and 20 minutes because it closes at midnight. Okay? All right. I will see you guys on Wednesday. And I'll leave this chat open if there's any last minute questions here.